Have you ever stopped to think about how your refrigerator or your air conditioner actually works? I mean, it really feels like magic, right? But it's not. It's engineering. And deep inside, there's this hidden blueprint, this super precise map that has to follow a very strict set of rules. Today, we're going to learn the language of that map. We're going to draw a perfect refrigeration cycle, step by step.
So what do we even mean by a perfect blueprint? Well, in engineering, perfect is everything. You see, a tiny mistake on this drawing, a line that's a little bit curved, a little bit off, that's not just a doodle. It actually represents a system that's inefficient, or maybe one that fails completely. So our goal here isn't just to draw some lines. It's to really get inside the logic of engineering perfection.
Okay, here's our game plan for today. We're going to build this thing in 4 key stages, covering every single part of the refrigerant's journey. For each step, we'll learn the super strict rule it has to follow. And then, at the very end, we're going to run a final validation check, just to make absolutely sure our design is flawless.
All right, let's dive right in. The real genius of this diagram is how it takes all this complex thermodynamics, the physics of heat and energy, and turns it into a simple visual map. We are about to translate the invisible laws of refrigeration into a drawing that is crystal clear and incredibly precise.
So our journey starts with compression. The refrigerant, which is a cool gas at this point, goes into a compressor. And the compressor's job is to just squeeze that gas, which makes its pressure and its temperature go way, way up. On our map, this is going to look like a steep, really organized climb from point 1 to point 2.
Now, the key word for this step is isentropic. I know, it sounds super complicated, but it just means the process is perfectly efficient. Think of it like this. In the real world, when you compress something, you get friction, you get wasted heat. That's chaos, or what scientists call entropy. But in a perfect cycle, we assume there is zero chaos, absolutely none. All the energy goes right into compressing the gas. That's what isentropic means, constant entropy, perfect order.
And that brings us to our very first critical rule. On our diagram, this perfect, orderly compression has to be a straight, inclined line. A super common mistake is to draw a curve here, but a curve would represent all those inefficiencies we just talked about, that wasted energy. So to be perfect, it's got to be straight. Precision is absolutely everything.
And the rule gets even more specific. The line has to slope upward and to the right. Why? Well, the upward movement shows the pressure is going up, and the rightward movement shows that the total energy, or enthalpy, is also going up. A vertical or horizontal line, that would mean one of those things isn't changing, which is just physically impossible when you're compressing a gas.
And the source material on this is crystal clear. There is zero room for error. It says right here, if the path from 1 to 2 is not a straight, inclined line, the whole thing is invalid. It's a binary world here. It's either perfect or it's completely wrong, no in between.
And boom, there it is. The first piece of our blueprint is officially in place. This line represents the refrigerant leaving the compressor as a hot, high-energy, high-pressure gas. Pretty cool, right? Now, let's see what happens to it next.
Okay, so now a refrigerant is this hot, high-pressure gas. Its next job? It's got to get rid of all that heat. This happens in what's called the condenser coils, like the warm coils you can feel on the back of your fridge. The goal here is to cool the refrigerant down until it becomes a liquid, all while keeping the pressure perfectly, and I mean perfectly, constant.
So how do you draw constant pressure on this map? Easy. You use a perfectly horizontal, straight line. Since the vertical axis on our graph is pressure, a flat horizontal line means the pressure value is not changing one bit. Any slope at all would mean the pressure is changing, which would be just plain wrong for this step.
And once again, the rule is absolute. This just shows you the unforgiving nature of these technical drawings. If it's not horizontal, it's invalid. Simple as that.
So let's add this to our diagram. You can see how the horizontal line from 2 to 3 just connects right onto our initial climb. The refrigerant has now successfully released its heat and has turned into a high-pressure liquid. Our blueprint is really starting to take shape now.
All right, next up is one of the most dramatic parts of the whole cycle, the expansion. The refrigerant, which is now a high-pressure liquid, takes this sudden massive plunge through something called an expansion valve, and this causes a huge drop in its pressure and temperature.
This crazy fast drop is called a throttling process and has this really unique property. The total energy of the refrigerant, its enthalpy, stays exactly the same. Here's an analogy. Think about water going over a huge waterfall. Its height, you could say its pressure, plummets, right?
but its total energy is the same at the bottom as it was at the top. It's the same idea here. Pressure drops like a rock, but enthalpy, which we represent with an H, stays constant.
So, to show this constant enthalpy process, our blueprint needs a perfectly vertical straight line. Since the horizontal axis is enthalpy, a line that goes straight down means the enthalpy value isn't changing at all. No exceptions, no slope, just straight down.
And, as you've probably guessed by now, the rule is just as strict as all the others. If that line isn't perfectly vertical, your whole diagram is invalid. It completely fails to communicate the basic physics of what's happening inside that little valve.
So with that vertical plunge now added, our blueprint is almost finished. We've tracked the compression climb, the horizontal cooldown, and now this throttling drop. What we have now is a very cold, low-pressure mix of liquid and vapor, and is ready for its final and most important job.
We have arrived at the final stage. The refrigerant is now this super cold, low-pressure mixture. And this, my friends, is where the magic happens. This is where it absorbs heat from its surroundings, which is what actually makes the inside of your fridge cold, and in doing so, it travels from point 4 all the way back to where we started, at point 1. And you know what? Just like when it was rejecting heat, this heat absorption also happens at a constant pressure. And that means our final rule is to draw another perfectly horizontal straight line, just at a lower pressure this time, to close the loop and complete our cycle. And there you have it. The blueprint is complete. Look at that. The isentropic climb, the constant pressure heat rejection, the constant enthalpy plunge, and the constant pressure heat absorption. 4 totally distinct processes, 4 incredibly precise lines, creating a perfect visual map of the entire refrigeration cycle. But hang on, are we really done? Not quite. In engineering, you always verify your work. It's time for the final inspection. Let's run a final validation check and see if our blueprint passes every single test according to the source material.
Okay, let's run the checklist, rapid fire. Is path 1 to 2 a straight inclined line labeled isentropic? Check. Is path 2 to 3 perfectly horizontal? Check. Is path 3 to 4 perfectly vertical? Check. Is path 4 back to 1 perfectly horizontal? Check. And finally, do the phase changes start and end right where they're supposed to? On the saturation lines? Yes, they do. Check. Our blueprint is officially 100% valid.
So, there we go. We've successfully mapped the hidden process that's happening inside your refrigerator right now. But this whole idea of translating a complex, invisible process into a simple, rule-based map, it goes way beyond just refrigeration. It really makes you wonder, right? What other critical systems, from aerospace to the stock market, rely on their own versions of these perfect, hidden blueprints just to function? Something to think about. Thanks for joining me for this explainer.